Hello. I'm Eric Landau. I'm the co-founder and CEO of Encord. Encord is an active learning platform for computer vision. We help companies building computer vision models across multiple industries, manage, annotate, and evaluate their training data. We work with some of the leading AI companies in healthcare, retail, agriculture, insurance, satellite, and more industries that are building computer vision models for production use cases. We're based in London, but have a very international team from some of the best tech companies and universities. So today we're going to be talking about active learning, and one thing that everyone is probably familiar with is these different screens. So you'll probably recognize some of these images. If you ever tried to log into a bank and you have to do a CAPTCHA, or the thumbs up and down button in ChatGPT. And believe it or not, these images are actually the future of AI. So what we're seeing is the iceberg of a continuous and corrective learning system by a big tech company that is trying to get their AI models to get better over time with user interaction. So when we're doing a CAPTCHA, we're actually acting as data labelers for models in production environments behind the scenes. And the issue is that very few AI companies have actually been able to achieve systems like this. The reason that few companies have built systems like this is they don't have models in production. So this is the gap between that's neat in an AI proof of concept model that might do a good job in a demonstration to investors, and that's useful. So something that many people can use consistently in an application over and over. And because AI technology is so new, there will just naturally be fewer companies on the right side of this gap. But there are other reasons why this gap persists. So the hard lesson that many companies learn between getting their models from a proof of concept state to the real world is that there is this additional set of requirements that come after you've already developed the first model. So these models have to be robust, they have to be reliable, they have to work in a very kind of general set of conditions. And they can't just be something that you turn on, you look at, try some experiments on and then shut down. They have to be systems which are maintainable and work when in collision with real world usage. So few companies are on the right side of the gap. Most are still in the that's neat category. And there's a few different types of these earlier stage companies. So the first ones that are just getting started are really building a pure proof of concept models. They often use open source tools or manual processes. Once they've graduated from that, they get some success, kind of proved the use case for what they're trying to do. They go into the next stage and they start the model development process in more seriousness. And most of these companies, their problem comes with collecting data and annotating data. So they have what we call the data quantity problem. But as these companies hit maturity and they get models into production and they build up massive piles of data, they realize that they actually need the right data to feed their models and the right labels to feed their models. And this is the data quality problem. So the best companies in the world leverage their own model infrastructure to address this data quality problem. They have what we call an active learning approach to model improvement. So what is this active learning approach? Well, we define active learning a little bit more broadly than most people do. Active learning, the way that we see it, it takes all the data problems that you have and it combines it together in an integrated strategy that is all done with respect to optimizing a downstream model. So instead of having these modular units where you collect data, you kind of randomly sample it, you label it, you train a model, then you test in production environment, all these things are integrated together such that every step that you're taking along the way is really in service of improving the downstream model that you have. And there's many reasons to use active learning in practice, lowering labeling costs, get better data prioritization, really kind of reduce the data overwhelm that a lot of these companies have. But there are some specific use cases that we see come up over and over again for different companies. The first is just selecting what data to annotate next. So you have a bunch of data, you just have to make some selection criteria. Oftentimes people just do it randomly, and kind of by first principles that there is a better way to do it than just randomly selecting it. The second is identifying label errors. So once you've selected some data to annotate and to label for your downstream model, you want to make sure that the labels are correct and that no errant labels will confuse your model in any way and bring down the eventual performance. And the last is finding model failure modes. So finding edge cases where the model doesn't really do a good job with respect to the data that you have in place and that you're testing in a validation sample or just generally outsampled in your production environment. And some of the leading companies have really, I wouldn't say perfected, but they've achieved these active learning systems. The Googles of the world, the OpenAIs of the world, DoorDash, for instance. These are the companies that are kind of leading the way with respect to model development. So going down to more specific active learning strategies that you can utilize to try to solve this data selection problem, this label error selection problem, and this model failure mode problem. What tends to be very, very useful is breaking down the data and really decomposing it into a more granular level, because it's very hard to understand terabytes and terabytes of data. So you have to slice it up in some way that you can digest and really reason about more effectively. And there's two main ways that we see people often do it. The first is class-based. So really decomposing the data as a function of your own labeling structure or ontology. So you might have cars, buses, pedestrians, bounding boxes in a data set, and you just want to look how everything does with respect to just the pedestrians. So that's doing the decomposition from an ontological perspective. But there's other questions that are relevant in your data that are not directly within your labeling structure. And these are more metric-based. So what are these metrics? Well, there are additional characterizations that might affect the quality of your downstream model that are not really encapsulated by just your labeling structure. And these come in various forms. So some easier ones to understand are things like the brightness of an image. So you might want to decompose your data sets that you have into how bright individual images are within that data set and index that data set over this one specific metric. And it might be that with this one specific metric, there's a correlate between that metric and either the rate of labeling error or the model performance itself. And you would want to know this and service this up as soon as possible. But there's a whole host of different metrics that we've seen people look at, and that we've looked at ourselves, that can be quite relevant. So we have this breakdown and categorization, different ways in which you can think about how to decompose your data, your labels, and also your model predictions. All right, so we'll go over 3 specific active learning strategies to address some of the problems that we went over earlier. Sampling data for optimal use in your model, then finding different failure modes within your model performance, and also identifying label errors that can be in your set of annotations. So the first is on data selection. There are many different strategies that people have used for more optimal data selection. One thing you can do is run a dimensionality reduction algorithm over embeddings, over the set of data that you have, or run clustering algorithms over the embeddings of the data in an unsupervised way. So you use some pre-trained model off the shelf, You just run that pre-trained model over your existing data, and then you run a clustering algorithm over the embeddings that are generated from that model. Then what you can do is just ensure that there's good samples from each cluster, just to make sure that from this kind of unsupervised perspective, the data is balanced for when it goes into the annotation step itself. So that's one example of a kind of strategy that you can enact to try to choose data with a certain criteria. And as you go annotate the data and train a model, you can then use now your model as the main embedding agent of the new data that comes in, rather than a pre-trained model that came off of the shelf. So you have this iterative loop with respect to data selection itself. Then there's identifying failure modes within the model. So what you can do as well is break down your data with respect to different metrics that you have a hypothesis might matter within your particular problem, and these can be computed orthogonally to your model development process. So something like brightness can just be computed with pure computer vision functions that you might find in OpenCV. And then run a correlation analysis between the metrics that you've run over the data and the actual model performance statistics against some ground truth that you have and that you're validating the model with. And we found that this strategy, you can often surface some very, very surprising relationships between different slices and decompositions of the data and the model itself. You can find things like, oh, my model doesn't do very well when stuff is extremely blurry, which is maybe not a very surprising conclusion, but it helps you really validate that blurry images are a problem and requires some specific intervention to improve over time. Then there's an example for a strategy of identifying label errors. We have this tiger now, which is erroneously labeled as a cow. And sometimes that just happens. If you run an annotation process, you get annotator fatigue, or you get some annotators that are not trained well to the task. And so these label errors can just end up flowing through into your training data and often get uncaught. So what's one strategy which you can then try to identify these potential label errors? Well, we can go back to an embedding approach. One idea is to embed the actual images within a particular bounding box, and then compare that embedding to all of its nearest neighbors in the latent space, and just check, does the categorization of that bounding box match its nearest neighbors or not? And if you have a bunch of correct tigers and you have this categorization of a cow, you can look at the embedding of this tiger, and it'll be a cow here, but it'll look at all its nearest neighbors. All my nearest neighbors are tigers. That's bad news for the cow, maybe in more ways than one. So that means that you should probably change that particular label. So using this metric approach, both with embeddings and just kind of breaking down and granularly decomposing the data, you can create these strategies which really improve and solve the different problems that we see people have a lot. And we've seen many, many different creative solutions to a lot of these issues. So we'll go over a particular parking management use case that we've seen and have worked with in the past. So for this particular use case, the company in question, they built their first model of a parking management system to really count the number of cars within a parking lot and really create an inventory of what cars are there and detect if there's any issues that go on within the parking lot. They built it within a set of initial parking lots within Boston. So they had some cameras mounted. They collected a bunch of data of the parking lots in Boston. They drew a bunch of bounding boxes over the cars there so that they have a good object detector to count all the different cars. And they built the first model that actually worked quite well on this parking lot, and hit all the performance criteria that they had with their client at the time, and they were quite happy. So having had some success at this location, the natural thing is, okay, let's expand this to more locations. Like, let's expand our business as well. So they mounted a bunch of other cameras in Santa Monica and Seattle. And then they realized, oh no, the same model that we worked with in Boston, it doesn't work as well in Santa Monica and Seattle and Minnesota. So what do you do in this use case where you're failing on the kind of generalizability aspect of this proof of concept to production gap? Well, they used this metric approach. So broke down the conditions of the images in the different sites that they had, because the model wasn't getting zero; it was doing okay, but there were certain subsets and use cases where it just wasn't really doing very well. And what they wanted to understand was, how could they have a theory over where their model was doing well and where it wasn't doing well within these new sites. And there was a kind of portfolio of metrics that they ran over the new sites to identify these different potential issues and see which conditions were such that the model just wasn't performing very well. And this was useful for a number of use cases. One, it kind of helped them understand their initial model a little bit better and where they could apply transfer learning in other sites that they might expand to in the future. But two, it identified and surfaced what subsets of data they needed to spend more time on with the model. And they needed to go in and annotate in the new sites in those conditions with a higher weight than more generally over all of the data that they had over the new sites. So they could really focus on the subsets, just select those for the annotation, and retrain the model on those use cases and get their model to perform better. So it's a combination of finding the model failure modes and also doing the optimal data selection in one. And that was really using this metric approach of finding ways to decompose the data, finding which ones correlated with your model performance, and using that information to prioritize the next set of data and run iterative model retrainings. So we've gone over some use cases, we've gone over metrics, and we think that active learning is really the key to closing the production gap that we see a lot of companies are currently facing. It's really to think ahead to what the Googles and the OpenAIs of the world are already doing, and building the model and training data infrastructure for the future, for not necessarily where you are now, but where you will be once your model works in the real world. And thinking from this kind of metric perspective is really going to put your application ahead once you start running into the problems that you get when you actually run into a production environment. And this comes from talking to many companies and quite sophisticated AI companies that have various models in production and went through the very difficult learnings of going from proof of concept to that state. Luckily, we've built some of the tools to help companies do that. One of our tools is on annotation. So really helping computer vision companies make the annotation process more efficient. But the second, what we're also very excited about, is our new active learning tool, which is free and open source, and which you can use today to really experiment and see if it can help with the type of model infrastructure and training data infrastructure that you have. And of course, we're very happy to talk to anyone that is interested in learning more about either of these things. We are a data labeling company that wants people to label less. I think we're the only data labeling company in the world that has that view. So thank you so much for the time today. I'm Eric. I'll leave the pip command for installing our open source tool at the bottom as a shameless plug in case you want to. Of course, feel free to reach out and speak afterwards. So thank you so much. Bye.